So we are back and we're still working through the DOE Volume 1. The last time we talked, we had reached a summary. In the last chapter, we talked about the different phases. And so sublimation was a change from solid to vapor. Vaporization was a change from liquid to vapor. Condensation was the change from vapor to liquid. And fusion or melting was the change from solid to liquid. So once we understood those phases, that brings us to the next topic, which is the property of diagrams and steam tables. So these properties are used in studying the theoretical and actual properties and efficiencies of a given system. So, the outcomes are, given the modular diagram and sufficient information, indicate the state of the fluid and determine any unknown property for a liquid. Then, given a set of steam tables and sufficient information to indicate the state of the fluid, we're going to determine the unknown properties for the fluid. And then also we're going to determine the change in enthalpy of the fluid as it passes through a system component, given the state of the fluid at the inlet and outlet of the component in either steam tables or a modular diagram. So let's get into some of the properties of a diagram. Okay, so the phases of the substances and the relationship between the properties are most commonly shown on these diagrams, and a large number of different properties are defined. And there are some dependencies between properties. For example, standard atmospheric pressure and temperature above 212 degrees Fahrenheit. Water exists as a steam, not a liquid. It exists as a liquid at temperatures of 32 degrees Fahrenheit and 212, and it exists as an ice at temperatures below 32 degrees Fahrenheit. So in addition to properties of ice, water, and steam, they are related. Saturated steam at 212 Fahrenheit and standard atmospheric pressure has a specific volume of 26.8 cubic feet per pound per mass. And at any other temperature and pressure, saturated steam has a different specific volume. For example, at 544 degrees Fahrenheit and 1,000 PSI pressure, the specific volume is 0.448 cubic feet pound per mass, So these 5 basic properties of substance are usually shown in property diagrams, and those are pressure, temperature, specific volume, V, specific enthalpy, and specific entropy. And so when a mixture of 2 phases such as water and steam is involved, a 6th property, quantity X, is also used. So there are 6 different commonly encountered property diagrams. There's the pressure temperature diagram, pressure specific volume diagram, pressure enthalpy diagram, pressure temperature diagram, temperature entropy diagram, and enthalpy entropy, or the Maillard diagrams. So let's start with the pressure temperature diagram. So a PT diagram is the most common way that we show phases of a substance. So in this figure below, this is the pressure temperature diagram for pure water. A PT diagram is constructed for any pure substance, and the line separates the solid and the vapor phases, and this is called the sublimation line. The line that separates solid and liquid phases is called the fusion line, and the line that separates liquid and vapor is called the vaporization line. The point where the 3 lines meet that was, remember talking in a previous chapter, is called a triple point. And this is the only point at which all 3 phases, solid, liquid, gas, are in equilibrium. The point where the vaporization line ends is called the critical point, and we looked at the critical point in the last chapter. We talked about inflection, or the point at which the graph changes direction. This is a concept that is further explained, in calculus, because they talk about points of inflection, points where graph changes direction, slope is equal to 0. So we discussed that in the last chapter. And at temperatures and pressures greater than those at the critical point, no substance can exist as a liquid, no matter how great of a pressure you exert on it. Okay, so out here, you can't have a liquid, no matter how much pressure you put to try to get those molecules to come into close proximity to one another, to organize themselves into the liquid state. You cannot have the liquid state past that critical point. Then we have the pressure specific volume diagram. Okay. And this is another common property diagram. This is figure 10. And this is for pure water. Okay. And this diagram, like the previous diagram, it can be made for any pure substance. A PV diagram is different from a pressure temperature diagram in one important way. There are regions on the PV diagram in which two phases exist together, which you don't see in the aforementioned diagram. Okay. So in the liquid vapor region on this figure, water and steam exist together. In the liquid vapor region, water and steam exist together. So for example, at point A, this point here, water with a specific volume given any point B exists together with steam with a specific volume V sub B at any point C. So they're just talking about this particular line, saying that this liquid and this vapor, that they coexist. Okay. And the dotted lines in figure 10 are lines of constant temperature. So these lines here, this line, this line. So we have this line, T1, and we have this line, T2. They're at constant temperature. So the quality of the mixture at any point of the liquid vapor region can be found because the specific volumes of the water, steam, and mixture are all known. The quantity can be found using the following relationship, where V is equal to X V sub G plus, in parentheses, 1 minus X V sub F, or they have rearranged this equation to get X by itself. So X is equal to V minus VF over VG minus VF. And that's also equal to V minus VF over VFG, where V is the specific volume, and that's in cubic foot per pound per mass. X is the quality of the mixture. It doesn't have any units. V sub G is the specific volume of the vapor, which is in cubic feet per pound per mass. V sub F is the specific volume for the liquid, which is in cubic feet per pound per mass. And V sub FG is a specific volume change of vaporization, which is in cubic feet per pound per mass, or V sub FG is equal to V sub G minus V sub F. Okay. So the pressure enthalpy diagram, a pH diagram, exhibits the same features of the PV diagram, right? So in figure 11, the pH diagram for pure water, a pH diagram can be constructed for any pure substance, just like we said for the last two diagrams, okay? And there are regions, I'm sorry, like on the PV diagram, there are regions on the pH diagram in which two phases exist together. Okay. So this looks very similar, if you look at this dotted line, to what you saw in your previous diagram, your PV diagram. All right, where you have this this phase, this liquid phase and this vapor phase, or steam, water and steam coexisting. So in the liquid vapor region in figure 11, water and steam exist together. So for example, at point A, this point here, water with an enthalpy H sub F given by point B exists together with the steam with an enthalpy of H sub G given by point C. And so the quantity of the mixture at any point in the liquid vapor region can be found using that relationship. So the enthalpy value, once they understand that these two phases, water and steam, coexist in this particular region, then they take the time to mathematically define it, where enthalpy is equal to H sub G plus 1 minus X over H sub F. They rearrange this equation to solve for X. So X is equal to H minus H sub F over HF sub G, and then they define the variables. So H is specific enthalpy of a mixture, which is the units for it is BTU per pound per mass. X is the quality of the mixture, and it has no units. H sub G is a specific enthalpy of the saturated vapor, which is in BTU per pound per mass. H sub F is a specific enthalpy of a saturated liquid, and that is in BTU per pound per mass. And H sub FG is the enthalpy change of vaporization, and that's also in BTU per pound per mass, or H sub FG is equal to H sub G minus H sub F. And so, like I said, this looks very similar to the aforementioned diagram. Sorry, guys. And then you have the enthalpy temperature phase diagram. All right. And this diagram exhibits the same features of the previous property diagrams, where you start to see, again, the line here and the coexistence of phases. So in figure 12, this is the HT diagram, or the enthalpy temperature diagram for pure water. An HT diagram is constructed for any pure substance. As in the previous property diagrams, there are regions where two phases exist together. And so the region where you have the saturated liquid line and the saturated vapor line, it represents two phases existing at the same time. Okay, so vapor and liquid. And the other, we said water and steam. Okay. So the vertical distance between the okay. So the vertical distance between the two saturation lines represents the latent heat of vaporization. Okay. So if pure water existed at point A, pure water existed at point A, on the saturated liquid line, and an amount of heat was added to equal the latent heat of vaporization, then the water would change phase from saturated liquid to saturated vapor that you see here at point B. So as shown with figure 12, the operation outside these saturated lines gives you this super cool liquid or superheated steam. So the quality of the mixture at any point in that region is mathematically defined as, as shown, is equal to H is equal to H minus HF over HFG. So these equations, hopefully you start to see that they are quite similar when you look at the boundaries where they have two phases that coexist. Hopefully you see a connection between how these equations are similar. Okay, so they didn't show you all the derivation or how they got X by itself with this equation here. They just showed you what the equation was. So hopefully you see that. Then you have the temperature entropy diagram, which is the one that I am, that I see the most. So this TS diagram is the type of diagram that is frequently used to analyze energy transfer or system cycles. So this is the graph that I usually would work with the most. Okay. And this is because work done by or on a system and the heat added to or removed from a system is visualized by this particular diagram. So by definition of entropy, the heat transferred to or from a system equals the area under the TS curve of a process. Okay. And so figure 13 is this TS diagram for pure water. The TS diagram can be made for any substance, and it exhibits the same features as this PV diagrams. Okay. And so this is the one that I am that we use the most as far as chemistry is concerned. And like I said, they talk about this area under the curve, right? This area under the curve. So we would actually integrate to figure out what this area under the curve. And also you can look at some pieces of equipment and they'll tell you, what the AUC is, or the area. In the liquid vapor region in figure 13, water and steam exist together. So for example, at point A, the water with an entropy of S of F at any given point B exists together with steam with an entropy of S of G at any given point C. The quantity of the mixture at any point in the liquid vapor region can be found using this relationship. So once they tell you what's going on in this particular region, which I'm circling, okay, and they're basically saying that, you can mathematically define this region because these two phases are coexisting. So S is equal to X S of G plus 1 minus X over X of F. And like I said, this looks like the aforementioned equation where you had, instead of these S's, you had enthalpy. So X, they got it by itself, is equal to S minus S of F over S F of G. So then they took the time to tell you what all of the variables mean for the equation. So S is specific entropy of a mixture, and the units are BTU per pound per mass per degree Rankine. X is equal to the quality of the mixture, and that's unitless. S of G is the specific entropy of the saturated vapor, that's in BTU per pound per mass per Rankine, or degree Rankine. S of F is the specific entropy of the saturated liquid, which is in BTU per pound per mass per Rankine, and S sub FG is a specific entropy change in vaporization, which is in BTU per pound per mass per Rankine, or S sub FG is equal to S of G minus S sub F. And then they get to the molar diagram, which is enthalpy, which is an enthalpy entropy diagram. And so this is shown in figure A1. of Appendix A. So you can go to that appendix in your in the back of your text. And this is a chart of enthalpy versus entropy. Okay, and normally, you know, in terms of chemistry, this isn't something that we plot, but of course, engineers would put would do a you know, a nice plot to put these two together. So this is more of an engineering way that they would graphically express this these two quantities so that they can analyze. So it's sometimes known that this HS diagram, it has an entirely different shape from those TS diagrams. And so the chart contains a series of constant temperature lines and constant pressure lines, and a series of moisture equality lines in a series of constant superheat lines. So the Maillard diagram is used only when the quality is greater than 50% for a superheated steam. Steam tables consist of two sets of tables of energy transfer properties of water and steam, saturated steam tables and superheated steam tables. Portions of these tables are shown in figure A2 of Appendix A, and both sets of tables are tabulations of pressure, temperature, specific volume, specific enthalpy, and specific entropy. The following notation is used in these steam tables. So some use V for a specific volume because there's little possibility of confusing the velocity. Okay. So T is temperature, which is in Fahrenheit. P is in pressure, the units are PSI. V is specific volume, which is in cubic feet per pound per mass. V sub F is specific volume for a saturated liquid, which is in cubic feet per pound per mass. And V sub G is a specific volume for the saturated vapor, and that is in cubic feet per pound per mass. V sub FG is a specific volume change of vaporization, and that is in cubic feet per pound per mass. H is specific enthalpy, that's BTU per pound per mass. H sub F, specific enthalpy of a saturated liquid, and that's BTU per pound per mass. H sub G is specific enthalpy of a saturated vapor, which is in BTU per pound per mass. H sub FG is specific enthalpy of change of vaporization, and that's BTU pound per mass. And then you have the entropy term. So S is specific entropy, that's BTU per pound per mass per degree Rankine. S sub F is specific entropy for the saturated liquid, that's BTU per pound per mass per degree Rankine. S sub G is specific entropy of a saturated vapor, that's BTU, that the units are BTU per pound per mass per degree Rankine. S sub FG is specific entropy change of vaporization, and that is also BTU per pound per mass per degree Rankine. And SH is a number of degrees of superheat, and that's in degrees Fahrenheit. So the saturated steam tables give the energy transfer properties of saturated water and saturated steam temperatures from 32 to 705.47 degrees Fahrenheit, which is the critical temperature. And for the corresponding pressure of 0.08849 to 3,208.2 PSI. And so normally these steam tables are divided into two parts. You have temperature tables, which list the properties of according to the saturation temperature, or T sub sat, and pressure tables, which lists them according to PSAT. Yeah, so figure A2, it shows, a portion of the typical saturated steam table and a portion of the saturated steam pressure table. And the values of enthalpy and entropy given in these tables is measured relative to the properties of the saturated liquid at 32 degrees Fahrenheit. Hence the enthalpy, or the H of F, of the saturated liquid and entropy, S of F, of the saturated liquid, have values of approximately 0 at 32 degrees Fahrenheit. So most practical applications using saturated steam tables involve these steam water mixtures. So this is a point at which these two phases coexist. So the key property of such mixtures is steam quality, which is represented by X divided by the mass of steam present per unit of mass of steam water mixture, or the steam moisture content, represented by Y, defined as the mass of water present per unit mass of steam water mixture. So the following relationships exist between the quality of the liquid vapor mixture and the specific volumes, and the enthalpies and the entropies of both phases of the mixture and of the mixture itself. And these relationships are used for those steam tables. And so they go ahead and show you how they mathematically defined it. So V is equal to X VG plus 1 minus X of VF. They get X by itself. So V minus V sub F is equal to, V minus V sub F divided by VFG. These look just like the equations for enthalpy and entropy, okay? So this equation, it looks very similar when you start talking about equality. H is equal to X sub G, we've already gone through these equations, plus 1 minus X times H sub F. And so this equation looks very similar to this one, where X is defined as H minus H sub F divided by H sub FG. And this equation for quality, when you start talking about entropy, looks exactly the same as well. So S is equal to X S of G plus 1 minus X times S of F. Get X by itself, that's S minus S of F divided by S FG, okay? So these equations, this one here, start talking about quality. This equation here, we start talking about quality with enthalpy and then entropy. Those equations look very similar because you're looking at a point on the graph where the water and steam, they coexist. So in order to solve problems in thermodynamics, the information concerning the state of the substance has to be obtained. Usually two properties, for example, V, P, T, H, S of the substance must be known in order to determine the other properties. And these properties are usually obtained utilizing that Maillard diagram we talked about before. Like I said, that diagram has enthalpy and entropy. That Maillard diagram has enthalpy and entropy. So these other properties, like I said, are obtained from the Maillard diagram if the substance is a steam, or if it's saturated, superheated, or if it's saturated or superheated. So the saturated and superheated steam tables can be used as well, and that's figure A1 and A2. So the following examples use the Maillard diagram as steam tables. So they ask the question, if you have a superheated steam at 700 psi and 680 degrees Fahrenheit, and you expand it at a constant entropy of 140 psi, what is the enthalpy? Okay, they ask you what is the enthalpy. So they use the Mayer chart and they locate point 1 in the intersection of 700 psi and 680 degrees Fahrenheit. And they read that H is equal to 1,333 BTU. So going back to that Mayer diagram, if you were to read it at 680 degrees Fahrenheit and 700 psi, the H is equal to 1333 BTU per pound per mass. If you follow the entropy line down vertically to 140 psi line, then you read that the enthalpy is 1178 BTU per pound per mass. So if you subtract 1178 from 1333, you get negative 155 BTU per pound per mass for the change in enthalpy. The next example is they ask you what's the specific volume, enthalpy, and entropy of a steam having a quality of 90% at 400 psi. From the steam tables, they show you that V sub F is 0.01934, V sub G is 1.4162, and H sub F is 424.2. H sub FG is 780.4, S sub F is 0.6217, and S sub FG is 0.8630. And they use the equation V because you're trying to figure out what the specific volume is equal to V sub F plus X times V sub FG, where if you were to plug them in, V is equal to 0.01934 plus 0.9 times 1.14162, and that's equal to 1.0468 pounds per mass per cubic feet. And when you solve for the enthalpy, which is H, because they ask for a specific volume, enthalpy, and entropy here. H is equal to H sub F plus X times H F sub G. H is equal to 424.2 plus 0.9 times 780.4, and that's equal to 1,126.56 BTU per pound per mass. And then, of course, if you find the entropy, S is equal to S of F plus X F of FG, where S is equal to 0.6217 plus 0.9 plus 0.8630, and that winds up being 1.3984 BTU per pound per mass per degree Rankine. Okay. So if the substance is not water vapor, the state of the substance is usually obtained using this TS diagram, which is entropy temperature, or HS diagrams, which is enthalpy entropy diagrams, available in any thermodynamic textbook for common substances. And I did show you guys. So I showed you guys earlier that, of course, not only do you have these diagrams, but they also compute some of these values as well. So the third example is if you use the HS diagram, mercury is used at a nuclear facility? What is the enthalpy of the mercury? If its pressure is 100 psi and its quality 70%. And so the solution is you look at the mercury diagram, A3, appendix A, you locate a pressure of 100 psi. You follow that line, reaching the quality of 70%, and the intersection of those two lines gives you an enthalpy of 115 BTU per pound per mass. So for the fourth example, if you use the diagram, carbon dioxide is used in a particular process in which the pressure of 100 psi and the temperature is 100 degrees Fahrenheit. And what they're asking you is what is the enthalpy value for that gas? So if you look at the carbon dioxide diagram in A4, appendix A, you locate the pressure of 100 psi. You follow that line to a temperature of 100 degrees Fahrenheit. The intersection of that line gives you an enthalpy of 316 BTU. So once various states have been fixed for a particular process, the substance is passed through, for example, going from a saturated liquid to a compressed liquid across a hump. Energy exchanges can be determined. Like what you saw in example 1, energy exchanges are never 100% efficient. Remember we talked about that. You don't have all of your fuel, for example, that gets converted into work. Some of that fuel is lost several ways when it comes to your cars. So you have exhaust, you have heat that's lost, and then of course some of the fuel goes into actually making the car. So the degree of efficiency obtained by the system depends upon the process through which the system has passed. Generally, efficiency of a component depends on how much friction exists in the flow of the substance, the pressure drop within the system, the inlet and outlet temperatures, and various factors. And the properties affecting the efficiency of the system are determined by use of the charts and diagrams mentioned. So when power cycles are utilized for like large systems, the efficiency of each component should be maximized in order to have the highest efficiency for that particular system. So each component affects the system efficiency in a different manner. And so to maximize the efficiency, the practical approach to large systems is to have multi-stage expansion with reheat between stages and regenerators in the system where it's applicable. It's the same thing with your car. 100% of your fuel doesn't get converted into work. You have exhaust where you have carbon monoxide, water that is lost. Then you have heat that is lost. So it's given off by the engine. So all of it doesn't go into making the car work. Some of it is lost through other things. Okay, so you start to understand that you don't have fuel efficiency. Summary. This is where you guys will take your notes. So take a few minutes here to notate any constants that you need to notate that you were given in the previous pages. Recording in progress. So you guys have worked on the summary sections in order to make sure that all the notes that you needed to add were there for the previous chapter. Now we're going to talk about the first law of thermodynamics. And this law is a balance between the various forms of energy as they pertain to a specific system that you're studying. So some of the objectives for this chapter is that they're going to state the first law of thermodynamics, use the first law, analyze the open system, And all the energy transfer processes that cross these boundaries use the first law to analyze cyclic processes for the thermodynamic system. And if your system is defined, perform energy balances on all the major components of that system. Given the heat exchanger, perform an energy balance across two sides of the heat exchanger. Identify the path on a TS diagram that represents thermodynamic processes occurring in a fluid system. So the first law states that energy cannot be created nor destroyed, only altered in form. So for any system, energy transfer is associated with the mass and energy crossing the control boundary. The example we used before was like bomb calorimetry, or what it takes to like make ice cream inside of where you have the ingredients inside of a container, and then outside you have the salt and ice, rock salt and ice. So mass and energy crossing this control boundary, external work and or heat crossing the boundary, and the change of stored energy within the control volume. Mass flow of the fluid is associated with kinetic, potential, internal, and flow energy that affect the overall energy balance of the system, and the exchange of external work or heat that completes this energetic balance. So the first law of thermodynamics is referred to as the conservation of energy principle, meaning that energy isn't created or destroyed, but it's just transformed into various forms as a fluid within the control volume is being studied. The energy balance that we speak of is maintained within a system that's being studied, and the system is a region in space, they call that the control volume, through which the fluid passes. The various energies associated with the fluid are then observed as they cross boundaries of the system and the balance that is made. So in the previous chapters, for volume 1, the system may be one of 3 types. It can be isolated, closed, or open. So the open system, it indicates mass, heat, and external work are allowed to cross the control boundary. The balance is expressed in words as all energies into the system are equal to all energies leaving the system, plus the change in storage of energies within the system. And so you recall, thermodynamic systems are composed of kinetic energy, potential energy, internal energy, flow energy, as well as heat and work processes. And so that was, in the aforementioned chapters. So this this Greek letter here is sigma, and sigma is used when we just add everything up. Okay, so this Greek letter here is sigma, and it's just used to indicate we add everything up. And delta, is usually when we do final minus initial. So the sum, sigma is usually the sum. The sum of all energies in is equal to the sum of all energies out, plus for delta, we call it change in energy stored in the system. So they're represented by sigma E in is equal to sigma E out plus delta E storage, okay? So for most industrial plant applications that use cycles, there's no change in the storage. The heat exchangers, they don't swell while they're in operation. Okay. So in the equation form, the balance appears as indicated in figure 14, where Q is the heat flow into the system, which is in BTUs per hour. So of course, you know that is a rate. So anything divided by unit time is actually a rate. MN is the mass flow rate. into the system, and that's pounds per mass per hour. UN is the specific internal energy into the system, and that's BTU per pound mass. PNVN is the pressure specific volume energy into the system, which is foot pound per force per pound per mass. And then the V squared, so this is a different V, N divided by 2GC is the kinetic energy into the system, and then that's in foot pound per force per pound per mass, where V is with this line over it. This line usually means that we're talking about an average. So whenever we put a line over a variable, we're talking about an average. So that's the average velocity in foot per second, where GC, remember we talked about this earlier, is the gravitational constant, and that's 32.17 foot pound per mass per pound per force second squared. Okay, so we talked about this this value in the previous chapters. G divided by GC times Zn is the potential energy of the fluid entering the system, and that's in foot pound per force per pound per mass, where Zn is the height above the reference level in feet. G is the acceleration due to gravity in foot per second squared, or feet per second squared. And GC is the gravitational constant, which is 32.17 foot pound per mass per pound per force second squared. Okay. So remember these constants because they were previously mentioned. W is equal to the workflow out of the system, which is in foot pound per force per hour. M out is mass flow rate of the system, which is in pound per mass per hour. Rate. Rates again. U out is the specific internal energy out of the system. That's in BTU per pound per mass. P out, V out is pressure, specific volume, energy out of the system. That's in foot pound per force, pound per mass. V squared out over 2GC is the kinetic energy out of the system, and that's in foot pound per force, pound per mass. And G divided by GZ times Z out is the potential energy out of the system, and that's in foot pound per force per pound per mass. So this is just a graphical representation of the first law of thermodynamics. You have the system boundary, you have energy that is coming in, the energy that is transformed, and the energy that is going out. And so they have shown you how they're able to look at a combination of these different types of energies that go into and out of a system, and combine them to come up with an expression for the overall energy that goes into and out of the system. See, all of that is in, all of that is out. And then of course, these are the energies that are transformed, because you don't ever have 100% efficiency, okay? You don't ever have 100% efficiency. So heat and work can be directed into and out of the control volume. And so that's what they're showing here. Heat and work can be directed into and out of the system. Okay, so that's what they're showing. So heat or work can be directed into or out of a controlled volume, but for convenience and standard convention, the net energy exchange is presented here with the net heat exchange, and it's assumed to be into the system, and the net work assumed to be out of the system. So they're just using ways to simplify the way they talk about how energy moves into and out of a controlled volume. So if no mass crosses the boundary, which is kind of like what happens with whenever you make ice cream, no mass crosses the boundary. So your ingredients don't leak out, hopefully. If mass, work, and heat do not cross the boundary, that is the only energy exchange is taking place within the system, then the system is referred to as an isolated system. And isolated and closed systems are nothing more than specialized cases of an open system. So in this book, the open system approach to the first law of dynamics is what's going to be emphasized because it's more general way of talking about a system. And almost all practical applications of the first law require you to have an open system. And understanding of the control volume concept is essential to analyzing a thermodynamic problem and constructing the energy balance. So the problems, they get more complex and more difficult when you're not talking about an open system. So they want to just go ahead and use that particular assumption so that the math and the equations, you don't have to make all these exceptions to the rule. So that's what they're saying. So two basic approaches exist in studying thermodynamics, and that's the control mass approach and the control volume approach. The former is the Lagrange approach, and the latter is the Eulerian approach. And so in control mass concept, a clump of fluid is studied with its associated energy, and the analyzer rides with the clump wherever it goes, keeping the balance of all the energies that are affecting that that clump of fluid. Okay, and that's what they're showing you here. They're looking at the isolated system or energy that changes within it. They're looking at the closed system. That's where you have controlled mass, and they're looking at the work that goes into and out of the system, the heat that goes into and out of the system. Okay, and then of course they have, just a visual way that they represent the open system. Okay, so with the open system, you see heat and work that are put into the system. You also see the changes in energy and mass that flow into and out of the system. So it's just a graphical representation to show you how the three systems are different. It's just a pictorial way to show you how the three systems are different. So the control volume approach is one where you have this fixed region in space, and it's established within a specific control boundaries, as shown in figure 14. The energies that cross the boundary of this control volume, including those with mass crossing the boundary, are then studied and the balance is performed. The control volume approach is usually used today in analyzing thermodynamic systems, and it's more important and convenient, and it requires much less work when you keep track of the energetic balances. Okay, so if you're not talking about this particular system, it's a little bit more difficult to use the mathematical approach because you have to make all these different exceptions. So it's more convenient and requires much less work. So examples of control volume applications, they are included in the in this figure. Okay, so here they have this centrifugal centrifugal separator, and they're just showing you how mass goes into a system, how work comes out of a system. So you have mass, M sub H1 that goes into the system. It also flows out of the system. And also you have gas that also flows out of a system. And you're basically tracking, what happens to a liquid inside of this particular centrifugal separator. Okay, and so like I said, they like to use the open system because it's just easier to handle when you start talking about the math. And here you have an open system with control volume. And here they're showing you a system where there's air, there's an air side and there's a CO2 side. They're showing the mass that's exchanged and the heat at the bottom that actually goes into the system. Okay, so this is another open system where you see that some mass is exchanged. And then they show you multiple control volumes within that same system. So they're trying to show you how the fuel reactor, the steam generator, the pump, how energy is exchanged between those systems. Okay, so they're trying to show you that this is definitely an open system because you see energy going in and out of the system, mass going in and out of the system. And because you can see that, you know, this is also graphically, they're trying to show you that this is an open system and this is why they use the equations that they use. Okay. So they're trying to show you work going into the system and then how mass flows into and out of the system. So they're trying to show you that this is an open system as well. So the forms of energy that may cross the control volume boundary include those associated with mass crossing the boundary. Mass in motion has potential energy, kinetic energy, and internal energy. So they're showing that these masses, they have potential, kinetic, and internal energy. In addition, since the flow is normally supplied by some driving power, which is, for example, a pump, there's another form of energy associated with the fluid caused by its pressure. So this form of energy is referred to as the flow energy. Okay, the PV work. This thermodynamic term is represented the various forms of energy that control the boundary with the mass that are given is M times U plus PV plus KE plus PE. And they're basically showing you how they are able to multiply the mass times all of these different types of energy that the mass in motion has. So in an open system analysis, the U and PV terms occur so frequently that another property, enthalpy, has been defined as H is equal to U plus PV. And this results in the above expression being written so, as M times H plus KE plus PE. And so in addition to mass and its energies, externally applied work, usually designated as shaft work, is another form of energy that may cross the system boundary. So in order to complete and satisfy the conservation of energy relationship, energy that is caused by neither mass nor the shift, no mass nor shaft work is classified as Q or heat energy. And then you can describe a relationship in the equation by using M times HN, PEN, KEN plus Q is equal to M times H out plus PE out plus KE out is equal to W. Okay, and then they define the variables. So M is the mass flow rate of a working fluid, and you know that every time you divide something by time, you're talking about rate. And as pounds per mass per hour, HN is specific enthalpy of a working fluid entering a system, that's BTU per pound per mass. H out is specific enthalpy of a working fluid leaving the system. So the first HN is entering the system, H out is leaving the system, and that's BTU per pound per mass. PEN is a specific potential energy of the working fluid that's entering the system, and that's foot-pound per force per pound per mass. KEN, KE out. KEN is the specific kinetic energy of the working fluid entering the system, and that's foot-pound per force per pound per mass. KE out is the specific kinetic energy of the working fluid leaving the system, and that's foot-pound per force per pound per mass. W is actually the rate of work done by the system. And of course, you see it's per unit time foot, pound per force per hour, and Q is the heat rate into the system. And so that's again divided by unit time, which is BTU per hour. So this first example illustrates the use of control volume concept while solving the first law problem involving most of the energy terms that were aforementioned. So we talked about how we were going to use the open system when we work these types of equations, and we talked about the balance of energy. So the enthalpies of steam entering and leaving the steam turbine are 1349 BTU per pound per mass and 1100 BTU per pound per mass respectively. The estimated heat loss is 5 BTU per pound per mass of steam. The flow enters the turbine at 164 feet per second at a point of 6.5 feet above the discharge and leaves the turbine at 262 feet per second. So we're going to determine the work of the turbine. Determine the work of the turbine. So the equation that will help you solve this problem is Mn times Hn PEN, Hn plus PEN plus KEN plus Q is equal to, M out times H out plus PE out plus KE out plus W. W is the rate of work done by the system. So we're going to divide out the M, since Mn is equal to M out. We're going to divide by M, since Mn is equal to M out. And once we do that, we're able to take that term out, okay, where Hn is plus PEN plus KEN plus Q is equal to H out plus PE out plus KE out plus W. Where Q is the heat added to the system per pound in BTU, pound per mass, and W is the work done by the system per pound, which is foot pound per force per pound per mass. Then we're going to use Joule's constant, where J, I think this was given earlier, is equal to 778 foot pound per force per BTU, for conversions and to substitute known values. So if we were to plug things in, 1349 BTU per pound per mass plus 6.5 divided by Joule's constant, which is 778 BTU pound per mass plus 164 squared divided by 2 times that constant 32.17 times 778 BTU pound per mass plus a negative 5 BTU pound per mass equals 1100 BTU pound per mass plus 0 PE out plus 262 squared divided by 2 times that constant of 32.17 times 778 BTU pound per mass plus W. And so the minus sign indicates the heat out of the turbine. Minus sign indicates the heat out of the turbine. So in order to solve for W, you have to get W by itself. So both sides are simplified, everything except for the unknown. So you have 1344.54 BTU per pound per mass is equal to 1101.37 BTU per pound per mass plus W. You get W by itself by subtracting 13.44 0.54 BTU pound per mass minus 1101.37, and you get the work is equal to 243.17 BTU pound per mass. So this example demonstrates that potential and kinetic energy terms are insignificant for a turbine, since the change in potential energy and kinetic energy is less than 1 BTU pound per mass. When the system, the fluid being studied, changes its properties, its temperature, pressure, and volume from one value to another as a consequence of work or heat or internal energy exchange, then it is said that the fluid has gone through a process. In some processes, the relationship between pressure, temperature, and volume are specified as the fluid goes from one thermodynamic state to another. The most common processes are those in which the temperature, pressure, and volume are held constant during the process. And so, like I said, when those are held constant, it makes the math just so much easier. So the most common processes, like I said, are where temperature, pressure, and volume are held constant. And those are classified as isothermal, which is where you hold temperature constant, isobaric, where you hold pressure constant, and isovolumetric, where you hold volume constant processes respectively. So iso means constant or one. And so usually when I would used to do problems, they would definitely put this in the line for the problem, so we would know exactly what we were holding constant, and that made the problems just so much easier. If the fluid passes through various states or processes, then eventually returns to the same state it began with, the system is said to have undergone a cyclic process. And one such cyclic process used is the Rankine cycle. And the two examples of this are shown in figure 19, which is towards your right side, the right side of this, right side on this page. So the processes that comprise the cycle are described below. AB is a liquid that is compressed with no change in entropy. And this is by an ideal pump. BC is constant pressure transfer of heat into a boiler. So heat is added to a compressed liquid. You have two phases, and you have the superheat state. A CD is where you have constant entropy expansion with shaft work output, and this is an ideal turbine. And then for a condenser, you have constant pressure transfer of heat in the sink, and unavailable heat is rejected to the heat sink. Okay, so not all individual processes the fluid must go through before completing the complete cycle, like the Rankine cycle that's discussed in greater detail later on the module. Figure 20 shows a typical steam plant. Heat is supplied to the steam generator or boiler, where the liquid is converted to steam or vapor, as in and the vapor is then expanded adiabatically. And that's one of the terms that we talked about earlier in the turbine to produce work, to produce a work output. So vapor leaving the turbine, it enters the condenser where the heat is removed and the vapor is condensed to a liquid state. The condensation process is the heat rejection mechanism for this because you have vapor that is condensed into the liquid state. The condensation process is heat rejection for the cycle. and the saturated liquid is delivered to the condensate pump, and then the feed pump, where its pressure is raised to the saturation pressure corresponding to the steam generator temperature, and the high pressure of the liquid is delivered to the steam generator, where the cycle then repeats itself. Okay. So with the example complete, it seems that it's appropriate to discuss the various components of a typical steam plant system. So although such system is extremely complex, only the major components will be discussed. So a typical steam plant system consists of a heat source that produces your thermal energy, for example, nuclear or fossil fuel, a steam generator to change the thermal energy into steam energy. So you have a complete steam plant that usually consists in connection with a steam generator in converting the steam into electrical energy, and then pumps to transfer the fluid back to the heat source. So you have reactor coolant pumps in the nuclear reactor, a pressurizer to ensure that the primary system maintains its desired pressure, and the necessary piping to ensure that the fluid passes through each stage of the cyclic process. So the steam plant is a large closed system. However, each component of the system is thermodynamically analyzed as an open system as the fluid passes through it. So the primary importance is the process of dissipating the energy created by a heat source. And this process takes place in the steam generator, which acts as a giant two-phase heat generator. The hot fluid from the heat source passes through the primary side of the steam generator, where its energy is passed to the second side of the heat exchanger in such a manner as to create the steam. The fluid, with its energy removed from the primary side, leaves the steam generator at a lower temperature and is pumped back to the heat source to be reheated. Each major component of the steam plant can be treated as a separate open system. Okay, and thermodynamic analysis of these various forms will be discussed, and it can be applied to a specific component in order to study its behavior. So a simplified example of thermodynamics involved in a steam generator is shown in these examples below. So an open system, you have a primary fluid that enters a heat exchanger of a nuclear facility at 610 Fahrenheit, and it leaves at 540 Fahrenheit. The flow rate is 1.38 times 10 to the 8th. If specific heat of the fluid is taken at 1.5 BTU per pound per force degree Fahrenheit, what is the heat exchange? What is the heat transferred out of the system by the steam generator? So they're showing you the same equation that you used in the last example, where Mn times H plus PE plus KEN plus Q is equal to M out, mass out, times H plus PE plus KE out plus work, or plus capital W. Neglecting potential energy and kinetic energy and assuming no work is done by the system, you can simplify the equation to M times Hn plus Q is equal to M times H out. Get Q by itself. Q is equal to M times H out minus Hn. So this took you through a way that we used to think about equations So we would use the conditions on that were a part of understanding this particular system. With this particular system, you had to understand that you could neglect potential and kinetic energy. You also needed to understand that no work was done on the system. And the main thing you need to understand is what equation is the final equation. Because if you go through all the derivation steps for these particular equations, you're gonna, make some mistakes. For Q, we can substitute MCP delta T, where CP is the specific heat capacity in BTU pound per mass. I'm sorry, BTU per pound per mass degree Fahrenheit. So MCP is, and we say delta T is T out minus T in. So we plug in 1.38 times 10 to the 8th pound per mass per hour times 1.5 BTU pound per mass degree Fahrenheit minus 540 minus 610. So Q winds up being negative 1.45 times 10 to the 10th BTU per hour, with the minus sign indicating that the heat out of the exchanger, which is consistent with the physical case. So this example, it shows you that the heat exchanger, the heat transfer rate can be calculated by using the equation Q is equal to M times H out minus H in, or Q can be calculated if we use the equation MC delta T. So it's important to note that the latter equation can only be used when no phase change occurs, since delta T is equal to 0 during the phase change. Okay, so we talked about the graphs earlier, especially when we're talking about latent heat. There's a time where the liquid is actually increasing in temperature. Then there's a time where the temperature is not changing because all the energy is being used to transform the phase. So we go from liquid, let's say, to gas. There's a time where the liquid gets hot, but once it starts boiling, then of course we can get to the point where we can produce the gas. So the temperature is not changing because the phase is changing. Okay, so that's why they're talking about delta T being 0. So the first equation can be used for a phase change heat transfer process, as well as a latent heat calculation. The pumps used for returning the fluid to the heat source can be analyzed as a thermodynamic system as well. One such example is this third example. So you have a coolant, and it's an open system. So a power pump is used to return the fluid from the heat exchanger back to the core. The flow rate for the pump is 3 times 10 to the 7th pound per mass per hour, with the fluid entering the pump as saturated liquid at 540 degrees Fahrenheit. And the pressure rise across the pump is 90 PSA. And so they're asking, what is the work of the pump? And some of the conditions for this particular problem, they're asking you to neglect heat losses and changes in potential and kinetic energy. Okay, so the conditions that they're asking you to include in how you calculate the work of the pump is neglect the heat loss and neglect the changes in potential and kinetic energy. So they give you that equation that was aforementioned. M times Hn plus Pen plus Ken plus Q is equal to M times H out plus Pe out plus Ke out plus W. They want you to assume that Q is equal to 0, right? Because you're neglecting heat losses, and they want you to neglect potential and kinetic energy. And that's what simplifies that equation. It takes out some of these terms, okay? So M times Hn is equal to M times H out plus W. If you get work by itself, W is equal to M times H in minus H out, where W is the rate of doing work by the pump. Okay, and so like I said, they're able to cancel some of the terms out because of the conditions that are placed on this particular problem. So W is equal to M times H in minus H out. H in is equal to U in plus VP in. H out is equal to U out plus VP out. So H in minus H out is equal to U in minus U out plus VP in minus VP out, which is also equal to delta U, okay, in minus out. So they represented this term by delta U is equal to VP in minus VP out. So since no heat is transferred, delta U, you can put a 0 in for it. And the specific volume out of the pump is the same as the specific volume entering the pump, since water is incompressible. So then they're still deriving this equation, okay? So H in minus H out is equal to V times P in minus P out. So you substitute the expression for work. Work is equal to M times H in minus H out. So if you were to substitute in for this particular segment of the equation, work is equal to M times V times P in minus P out. All right. And so they went through all of these derivation steps so that you knew to use this last equation. Okay, so they went through all of these steps. It showed you what the conditions do to that first equation to get you to use this last equation right here on line 4. So if you were to see those conditions, it needs to signal to you to use this. This is what you need to use. So if you go through all of these other steps, you're going to get confused because you're not going to know that based on the way the problem is written, they just want you to use this. Okay? You won't get confused if you do all of the aforementioned steps. So what they're doing is a derivation, an extensive derivation, and it gets even more complex than this. Just to tell you to use the equation, work is equal to M times V times P in minus P out. So using 0.01246 for your specific volume, so that's what you plug in for V. You have work is, W is equal to 3.0 times 10 to the 7th pound per mass per hour times 0.01246 cubic feet per pound per mass times negative 90 psi. And remember, you guys discovered that this 144 is actually a conversion factor. So it's 144 inches squared per foot square divided by 778 foot pound per force per BTU. So work is equal to negative 6.23 times 10 to the 6 BTU per hour, or negative 2,446 horsepower. So the minus sign indicates that the work put into the fluid by the pump. So this minus sign indicates work put into the fluid by the pump. And they give you this conversion factor for conversion between horsepower and BTU per hour. So they give you that conversion factor again, which this was aforementioned in some of the earlier text. This was aforementioned in some of the earlier text. So let me just remember. Okay, so they did all of this, right? They did all of this to show you to use the equation on line 4. So you need to get comfortable looking at the problem looking at the exceptions if you neglect heat loss and changes in potential and kinetic energy. And they go through all of these steps and tell you that that equation, because of those conditions, this is what you need to use. Okay, so you will waste time if you go through all of those different steps to derive the equation that you need. A thermodynamics balance across a reactor core gives an indication of the amount of heat removed by the coolant that is given off by the fuel rods. So they give you another example. The thermodynamic balance across a heat source. So they say in a particular facility, the temperature leaving the reactor core is 612 degrees Fahrenheit, while entering the core is 542 degrees Fahrenheit. Coolant flow through the heat source is 1.32 times 10 to the 8th pounds per mass per hour, and the specific heat of the fluid is 1.47 BTU per pound per mass degree Fahrenheit. So how much heat is being removed from the heat source? Potential energy and kinetic energy are small compared to the other terms, and so they are neglected. And so they're going to go back through another derivation because they've given you some conditions. Okay, so they're going to give you this equation that you've seen before. M is equal to, M times H times PE times KE, and they just write this little N here to let you know that all of these are N, plus Q is equal to M times H plus PE plus KE out. Of course, you saw in the earlier equations, all of these energies are out or coming out of the system, plus W, and Q is equal to M times H out minus HN. Substituting Q is equal to MC delta T, where CP is the specific heat capacity. Q is equal to M times CP times temperature out minus temperature in. Q is equal to 1.32 times 10 to the 8th pounds per mass, pound mass per hour, and then times 1.47 BTU pound mass degree Fahrenheit, and then they subtracted the temperature, 612 minus 542. So Q is equal to 1.36 times 10 to the 10th BTU per hour. Okay, so for example, for this example, Q is equal to MC delta T, and that was used to calculate the heat transfer rate, okay, since no phase change occurred. So you can use this equation when we start talking about no phase change occurring. All right, however, Q is equal to M, H out, H in could have also been used for the problem data that included inlet and outlet enthalpy. So they're just saying that there was another equation that could have been used to solve this particular problem. Okay, so they're saying that you could have used both of these equations to solve this particular problem. So the individual principal components of a reactor system have been thermodynamically analyzed, and so if all the components are combined into an overall system, the system could be analyzed as a closed system. And so this is shown in the following. So here they have a nuclear facility, the primary side, and it's to be studied as a complete system. The heat produced by the heat source is 1.36 times 10 to the 10th BTU per hour. The heat removed by the heat exchanger steam generator is 1.361 times 10 to the 10th BTU per hour. Rates. And so what is required? What is the required pump power, to maintain a stable temperature? So W P is pump work. QC is the heat reduced by the heat source, and then Q is the heat transfer from the generator. They give you the aforementioned equation, well, the equation that looks like the equations you use for the other problems, but of course the conditions change what gets zeroed out. So M times H plus PE plus KE plus W plus QC is equal to Q sub SG plus M times H plus PE plus KE. And for a closed system, the mass entering and leaving the system is zero. Therefore, this M is constant. So the energy entering and leaving the system is zero, and you can assume that kinetic and potential energy are constant. So you can zero out some of these terms. So QC plus WP is equal to Q sub SG. Get WP by itself, and that WP is equal to QSG times QC. So they're doing all of this, mathematical derivation and zeroing out of terms based on the conditions that they gave you, so that they can show you what equation that you really use. So they're showing you that you start with this, you start applying all the conditions, start zeroing out terms, but the equation that you're really going to use is right here. QC plus WP is equal to QSG, okay? So they derive these equations. And like I said, when you start deriving them, you can, really, take it up a couple of notches. So WP is equal to QSG minus QC. If you plug in, you subtract 1.361 times 10 to the 10th BTU per hour minus 1.36 times 10 to the 10th BTU per hour, and you wind up with 1 times 10 to the 7th BTU per hour. Or if you were to express that in horsepower, WP is equal to 4,007 horsepower. Okay, so they use that conversion factor on the answer. They use the conversion factor on the answer. Okay. So of the examples just completed, emphasis is placed on heat exchanger analysis. Both the primary side and secondary side have their own energetic balance, and heat energy is transferred from one fluid to another. In calculating heat exchanger heat transfer rates, we found that we could use Q is equal to MC delta H. Okay, so in the other problems, they use Q is equal to MC delta T here. We see that in place of that delta T, we use delta H. So perhaps a short analysis of the secondary side of the heat exchanger will aid in you understanding the heat exchangers important to the energy conversion process. So here we have another problem. So now they're looking at the secondary side of heat exchangers. Steam flows through a condenser at this particular rate, which is 2 times 10 to the 6 kilograms per hour, entering as a saturated vapor at 40 degrees Celsius. H is equal to 2,574 kg per kJ per kg, and leaving at the same pressure as supercooled liquid at 30 degrees Celsius, where H is equal to 125.8 kJ per kg. And cooling water is available at 18 degrees centigrade or 18 degrees Celsius. H is equal to 75.6 kJ per kg. Environmental requirements limit the exit temperature to 25 degrees Celsius, where H is equal to 104.9 kJ per kg. Determine the required cooling water flow rate. And so thermal balance gives us this following equation: QST sub STM is equal to negative QCW, where M STM times H out minus H in STM is equal to MCW times H out minus H in and a CW. So Then they get this MCW here by itself. So MCW is equal to negative MSTN HN minus H out STM divided by H out HNCW. And then they plug in and solve. Okay, so negative 2 times 10 to the 6 kg kilograms per hour times 125.8 minus 2574 kg per kj per kg divided by 104.9 minus 75.6. And so this MCW is equal to 1.67 times 10 to the 8 kg per hour. So in this example, you're calculating the flow rate using equation Q is equal to M delta S. The phase change occurred when the steam was condensed to water. Okay, and so Q is equal to MC delta T. That equation would have worked since the change in temperature is 0 when you have a phase change. So you either change in the temperature or you not, or the temperature changes 0 because you change the phase. So they had attempted to solve the problem using Q is equal to MC delta T. They would have discovered errors since delta T is equal to 10 degrees centigrade. The delta T is the delta T for subcooling a liquid from saturation at 40 degrees Celsius to a supercooled value of 30 degrees Celsius. Therefore, heat transfer process to condense the steam to a saturated liquid has not been taken into account. And so for the summary table, you want to go back through. You don't want to take the entire derivation for these equations, but you want to notate conditions and what some of the final equations that you use to solve the problems are. Because you want to get used to, if they state certain conditions, don't go through the entire derivation process. You just know what the final equation that you need to use is. And so you understand, like, I have everything I need to solve this equation. I know what to plug in. So go back to the conditions, go back to that final equation that's used to solve the problem, and put that in your notes.